For chapter 6, we are still going to continue our discussion on probability, but we'll look at a different type of distribution and how we can utilize that distribution to help us find different probabilities. In chapter 5, we looked at a discrete probability distribution, and with chapter 6, we're looking at a probability distribution that represents continuous values. So with section 1, we'll look at identifying the properties of a normal distribution. We'll find the area under a standard normal distribution given various z-values. So the z-score comes back again from chapter 3. And then we look at finding probabilities using a standard normal distribution. So that's what you have to look forward to in section 1 of chapter 6. So before we begin, first let's kind of talk about a normal distribution. In chapter 5, you looked at a discrete probability distribution which more or less looked like a histogram. And so this is a normal distribution. In a normal distribution, we want to be able to recognize some characteristics. And the first characteristics is the shape, and it's bell-shaped, right? The shape is created because of certain attributes. And when we were discussing histograms back in chapter 2, we talked about what creates the shape of the histogram as it related to the mean and the median and the mode, and how the data is being distributed across, how the data is being distributed. So for a normal distribution, we have the mean, the median, and the mode are equal, and they are at the center of the distribution. So here, where we see the Greek symbol mu stands for mean, this actually, the center of this distribution, the value for the mean and the median and the mode are all equivalent. They're all the same. This distribution is also considered unimodal, which means it only has one mode, and the distribution is also symmetric about the mean. And essentially, the symmetry tells us that it's the same on both sides of the mean value. So here we'll talk about the percentages in a little bit. This average, because it's the same value as the median and the mode, it divides the distribution into two equal parts. So we have the lower half and the upper half. One kind of characteristic that sticks out is that the curve here is continuous, right? So we look at this curve as being continuous. And also, we are going to get into the kind of a more or less an area model. Another attribute of this distribution is that the total area under the curve is considered to be 1 or 100%. So much like in the probability distribution where we had the histogram, those rectangular bars that contained the probability of an event, and when we add those probabilities together, we got 100% or 1. We can kind of view this in sort of the same aspect. And another feature that I didn't write down here is that this is, since it is continuous, this will continue to expand outward both in the right and in the left, and it will never actually touch the x-axis. It will just approach and get very, very close to it. So other features we want to be able to talk about, things that we haven't discussed since chapter 3, is the concept of a z-score, or in this case, the number of standard deviations a value is above or below the mean. And so here in the distribution, we can see that different parts of it is partitioned off with a percentage in it. And so that helps us start to look at this as kind of an area model. So if I kind of color in this middle section, this represents one standard deviation above and below the average value. And this distribution tells us that about 68% of all data, as long as it is normally distributed, is one standard deviation away from the average value. So as long as the situation models a normal distribution, then we can guarantee that about 68% of the data lies within one standard deviation. And then as we move outward from the mean, and we get 2 standard deviations away, we contain more of the data. So if I go out to 2 standard deviations, so that represents this portion that I've shaded in orange, that is about 95% of all the data. So if we look at a distribution we look at a distribution that's normally distributed, and we'll look at some examples here later, we can guarantee that as long as the distribution can be modeled by this bell-shaped symmetrical distribution, that 95% of all the data within that distribution lies within 2 standard deviations of the average value, where the average is in the center. And then we can go even further out, and we can look at 3 standard deviations, which is about 99.7% of all the data. Now, we won't be able to determine 100% of the data because, as I said earlier, that it doesn't stop here at 3 standard deviations. It actually continues to stretch out. So the area just gets less and less in the tails as it continues on and on forever. Generally, we just look for data values that are within 3 standard deviations because that encompasses almost all of the data set. 99.7 is near 100. So that's generally how far we go out to when we look at normal distribution. Now, I did mention z-score earlier, and we have to remember that the z-score represents the number of standard deviations that a value is above or below the average value. So if you recall this formula from chapter 3, we have value minus mean, which is x minus mu, divided by standard deviation, which is sigma. So that's a formula that you will be very familiar with, and you will use a lot in section or chapter 6, each section 1, 2, and 3. And then when we get into the last unit, which is unit 4, you'll use the z-score formula a lot in chapter 7 and chapter 8. Now, the distribution we looked at before was a normal distribution. So the only difference in the normal distribution is the horizontal x-axis. In this case, it's no longer considered x. It's actually considered the z-axis because these are z-scores. And then I'll talk more about that when we get into utilizing the normal distribution and the standard normal distribution to help us find the area under the curve for certain values, and then also to help us find probability. But the main thing that we want to be able to look at here is that this distribution has the same characteristics and attributes as a normal distribution. So all the same things that I wrote down before apply to this distribution. The only thing that's different is the scale of the axis, the horizontal axis, because now it will always be centered at 0, which is a standard deviation. So the average would be like no standard deviations, 0. And then as we move away from the average, this is represented in z-scores instead of actual values. And so we'll talk more about that in actually section 2 of chapter 6. In this section, it's only how can we use this distribution to help us find the area under the curve given certain z-scores. So if we're given certain values down here, how can I find the area under the curve knowing this information we talked about earlier, that 68% of the data is between 1 standard deviation, so 34 and 34, and then about 95% is within 2 standard deviations, so an additional 14 on each side, and then about 99.7% is within 3 standard deviations. So we're going to use that fact to help us not only estimate the area under the curve, we're also going to utilize a table E, which is something new for you. I know you were exposed to the binomial distribution table, so I'm going to show you a new table today, and you're going to utilize that table to help us find a more accurate area under the curve as well. So let's look at our first 2 examples. It says find the area under the standard normal distribution curve. It says to the left of z equals 2.22. Well, the first thing I want to do is actually draw out this standard normal curve, right? So the standard normal curve is a bell-shaped distribution, and when we have the z-scores written down, so 0 is at the center, and then 1, 2, and 3 represents 1, 2, and 3 standard deviations, and then -1, -2, -3 below the average and above the average. So what we would like to do is find this number, this z-score on the z number line here, which is between 2 and 3. So it's not quite halfway, so I'll make a little marking here, and it's to the left, so we want all the area below that number. So I'll shade that in. Now, what we could do is I really like to get into estimating. So when we find the actual value, we can compare and see how good our estimate was. So based on what I previously talked about, the center of the distribution divides it into two equal parts. So if I kind of divide this up, I know that this left half over here represents 50% of the distribution. And then I can further partition it off from 0 to 1 standard deviation according to what we looked at previously. That is about 34%. And then I can move another standard deviation. So between 1 and 2 standard deviations, that's about 14%. Now, it will be kind of difficult to estimate this here because from 2 to 3 standard deviations is a little bit over 2%, but here I'm not quite at 3. I'm a little bit less than halfway, but I really can't say that this is half of the area because this height of the curve is a lot higher than this height of the curve. So my best estimate is going to be able to use the 50%, the 34%, and the 14%. So when I add those values together, the estimated area is going to be about 0.98 or about 98%. Now, we can actually find a more accurate area if we use table E, which is the standard normal distribution table. Much like the table that you looked at for the binomial distribution, this table will help us find not only the area under the curve for certain z-score values, but it also is used as a probability table as well. So I'm going to show you how to utilize that. If you go to eCampus, and here's table B, the one we looked at previously, but we want table E. So you click on that link, and it will open up the z-score and probability table for you. And here it says table E, the standard normal distribution, cumulative standard normal distribution. So you have z-scores directly on the left side, left column. These are all z-scores to the to 1 decimal place, and then anything at the top will be the 2nd decimal place. So a z-score, well, I'll just go. If you look at this standard normal distribution down here, it's showing you that every single value within the body of the table, so every number, all these 4 decimal places, represents this area that's shaded in. So these values are only the area to the left. This table will only ever give you the area to the left of a z-score, never to the right. We have to do something to find that. So those are for the negative z-scores. For the positive z-scores, and again, down at the very bottom of the table, it shows you a z-score that is on to the right side of 0, meaning a positive value. So that represents these z-scores here, and this shaded in blue area represents all of these values in the table. So each value in this table is represented by this shaded in area here. So if we go back to our image that we created, or that I created, I want to find this area here that's shaded in red. I'm estimating the area to be 0.98, and all we need to do is locate this z-score on that distribution, so on that table. So to do that, it's positive 2.22, so here's 2.2, and if I go up to the top, this would be 2.20, 2.21, 2.22. So it would be the 3rd value in my table, so it would be here, 0.9868. That would be the area to the left of 2.22 when I go when I calculate that utilizing table E. So using table E, the area was 0.9868. And so that little bit of a difference between what we were able to estimate and what the actual table is according to the standard normal distribution table is because we weren't able to accurately estimate this value here. So it's kind of hard to estimate that part, but we can see within reason that the value, or that the number that we got is pretty reasonable, because at least visually we can tell that this number kind of matches what we have shaded here. So estimation will help you at least determine the reasonableness of your answer. So let's look at another example. We want to the right this time. So this was to the left. Now we want to the right of this z-score. So again, I make my standard normal distribution, 0, 1, 2, 3, negative 1, negative 2, negative 3. I want to find approximately where might negative 1, 2, 3, 9 be located. Well, I know it's between negative 1 and negative 2, not quite halfway, so I'll put it closer to the 1. And I want it to the right. So I want all this area to the right of this value. So anything greater than that number. Now again, I want to use estimation, so I locate the center of the distribution, and that means anything above 0 is the upper 50%. So already we know that the area should be more than 50%. And then from 0 to negative 1 is about 34%. Now it would be kind of hard to estimate this little sliver here. Again, it might look like it's halfway, but we really have no way of, we can get a reasonable estimate. We know that it's going to be more than 0.84 or 84% because of this little amount here. But I don't know, even though this is 14%, about 14%, I probably wouldn't be safe to say that, oh, this must be 7% because it looks halfway. Again, this little height, this bar is a lot taller than this bar. And it may very well could be 7%. And we can just at best get a better estimate by doing that. But the estimated area that we could go with right now is anywhere from 0.84 to probably 0.88 or 0.90. Right? Those are good estimates for the area that we should expect when we look at table E. Now the problem with table E, so I'm actually going to go to this z-score in table E, so negative 1.39. So I'm going to do that. So here is, no, that's not negative. Here's negative 1.3, and then 9 is all the way at the end. So I go up to the top of here's 0.09. So it's like you're taking this number and you're adding it, or you combine it with this number, and you get negative 1.39. And so this is the area that it's given me, which is not anywhere near the area that we found. And that is because that this area, again, is the area to the left. So when I go back to my table here, then the value that we have, that 0.0823 that's in the table, well, that's the area in the white, right? That's this area. I want the area in the brown. So if the entire distribution, everything under the curve represents 100% or 1, well, I would take 1 minus the area in the white, and that would give me the area that I want in the brown, which is 0.9177. So this is very close to the amount that we estimated, just utilizing the information that we talked about earlier, which is consistent with all normal and standard normal distributions as far as how much area is in between each of the standard deviations. So we can get a pretty good estimate utilizing that information. So for our last two examples, we'll look at how we find the area between two z-scores. So in this case, we have the z-score for for 0 and 0.98. So we want to find the z-score for that. Oh, we don't want to find the z-score. We want to find the area for that. So in this case, again, draw the normal distribution. Mark off the number of standard deviations. And then find where we're going to do our shading. Now, I do feel like it's necessary to actually sketch out the normal curve. It definitely helps you determine, or at least visualize, what realistic answer should you be getting. So 0, so I want the area here. I want the area in between those two. Now, we already know that we could pretty much estimate this pretty quickly because this is almost exactly one standard deviation above the average. And according to what we looked at earlier, that's 34% or about 34%. So we could say that the estimated area is 0.34 or 34%. Now, in order to find the actual area, I'm going to have to look at two z-scores in the table. So I want to go to the z-score of 0 and then a z-score of 0.98. So when I go back to the table E here, I want to go to 0, and that means the area to the left of 0 is 0.5000, 0.50, or 50%, which visually we could see that. That's not, really didn't need the table for that one per se. So if I go back here, the area for 0 is 0.5000, right? That's 50%, which should make sense because 0 is supposed to be the center of the distribution. So anything to the left of that would be 50%. Now we want to look at 0.98 as well. So we'll go back here and we'll go find 0.98. So here's 0.9, and then 8 is right here. So that's 0.98, which means the area to the left of 0.98 is about 84%. And again, that should make sense because we looked at earlier that anything below 0, 50%, anything within 1 standard deviation, 34%. So add those together. This is about 84%. So 0.8365. So if I write this on my distribution, then the area in the white here is 0.500, and then the area that's actually to the left of this brown line is 0.8389. Anything to the left of that brown line is 0.8389. That includes the white and that includes the green. So if I want to get the area in between those two values, or if I want to get only the green area, then we need to be able to subtract those two numbers. We subtract them and we get 0.3389, which is very, very close to the value that we estimated. It's more or less 34%, but we want to leave the value to 4 decimal places. And so this is more or less the 3 different cases and how you would be expected to find the area under a normal distribution. You either would need to be able to locate the area to the left of the z-score, or you would need to locate the area to the right of a z-score, or you would need to locate the area between 2 z-scores. Now, one thing we can also utilize this distribution for is a probability distribution curve. It's essentially the same as what we've been doing. Right? So we look at this as now I want the probability that the z-score is greater than 2.51. So in that case, well, I'd still drop my distribution, standard normal, mark off the z-scores, figure out where about might 2.51 be located. It's between 2 and 3. It's halfway between 2 and 3, and I want greater than, so I want this little area here. And if I estimate that, well, I know that anything below 0 is 50%, anything between 0 and 1 is 34%, and anything between 1 and 2 is 14%. That means that anything above 2 is about 2%, a little more than 2% actually, because I rounded between 1 and 2 is about 13.6, but I rounded to 14. So my estimated area is going to be most likely less than 2%. That's what I expect. I expect that when I calculate this, it's going to be a number less than 2%, probably even less than 1% to be in reality. But we find the probability the same way. We look for this z-score in our table, in table E. So let me go to table E, 2.51. So here's 2.50 and then 2.51, and it's telling me that the area or probability is 0.9940. And so you have to stop and ask yourself, well, would that make sense? Did I shade in 99% of the distribution? And we didn't. We only shaded in a small little tiny piece. So in that case, we have to remember that that 0.994 represents this distribution down here. So it's everything to the left of that z-score. And we want to the right of the z-score because it says greater than. So I need to take that and subtract it from 1, and I get 0.0062, which is 0.62%. So less than 1%, which is definitely less than 2%. So this is for the first part of your homework in section 1 of chapter 6. You're only utilizing the table to calculate the area under the curve or the probability for different instances. So whether it asks you to find the area to the left, to the right, or between, these are the cases. And if it asks you to find a probability, it's no different than asking you to find the area to the left, to the right, or between. You just have to pay careful attention to the symbols here. So if it's greater than, that one's to the right. If it's less than, that's to the left. And if it has two values in the probability statement, that will be the area in between. And then when we get into section 6.2, we look at how do we apply the concept of the normal distribution to more application real-world problems. So we'll look at that in the next lecture video.